Hi everyone, welcome to today's video, where we're going to dive into the world of CPU performance and embedded systems. So by the end of this video, you'll understand how CPUs work, what makes them faster or slower, and how small computers called embedded systems are used in everyday devices like cars and microwaves. Let's get started. Before we jump in, let's talk about what we're going to cover. By the end of this video, you'll understand the role of cache memory in CPU, be able to explain how clock speed, cache size, and the number of cores affect CPU performance, know what embedded systems are, and see more real-world examples. So let's start by looking at what's inside a CPU. Okay, so inside a CPU, there are several key components that work together to process data. First, we have the control unit. Think of the control unit as a manager of the CPU. It decodes instructions and controls the timing of operations. Next, we have the arithmetic logic unit. This is where all the calculations and logical operations happen. If the CPU is a factory, the ALU is the worker doing the math. Then there are registers, which are small, fast storage locations for temporary data. For example, the program counter keeps track of the next instruction to be executed. The memory address register holds the address of the data to be fetched. The memory data register stores data retrieved from RAM. And the accumulator stores the results from the ALU. So in summary, the CPU is like a well-organized factory, with each component playing a specific role to keep things running smoothly. Now that we know what's inside a CPU, let's talk about what affects its performance. There are three main factors. Clock speed, so how fast the CPU can process instructions. Cache size, the amount of fast memory available for quick data access. Number of cores, this is the number of processing units inside the CPU. Think of a CPU as a chef in the kitchen. The clock speed is how fast the chef can chop vegetables. The cache size is how much counter space the chef has to work with. And the number of cores is how many chefs are working in the kitchen. The more chefs and the more counter space you have, the faster you can prepare the meal. Let's go right to the basics then. So the speed of a processor is measured in hertz, abbreviated as Hz. So 1 hertz means 1 cycle per second. Think of it like a clock ticking once every second. If a processor runs at 1 hertz, it can complete one instruction, one basic task every second. Now that's extremely slow compared to modern computers, but it's where everything begins. Now 1 hertz is way too slow for today's tech, so we scale up. Just like 1 kilometer is 1,000 meters, 1 kilohertz is 1,000 cycles per second. That means a 1 kilohertz processor can handle 1,000 instructions every second. It's already getting a lot faster, but we're still just scratching the surface. Next up is megahertz, or MHz. Mega means a million. So 1 megahertz is 1 million cycles per second. Old computers from the 90s ran in megahertz. Imagine a million tasks happening every single second. That's actually pretty fast. But finally, gigahertz. Giga stands for billion, meaning 1 gigahertz is 1 billion instructions or cycles per second. That's the speed range of modern processors. So when you see a phone or laptop with a 2.4 gigahertz processor, it's performing 2.4 billion operations every second. Next, let's talk about multi-core processors. A dual-core processor has two processing units, or cores, in one CPU. A quad-core processor has 4 cores. The advantage of multiple cores is that they handle more tasks simultaneously, which improves performance. For example, a quad-core processor can be up to 4 times faster than a single-core processor when running multiple programs. Think of it like a single-lane road versus a 4-lane motorway. The motorway can handle more cars, or in this case, tasks, at the same time. Now let's talk about cache memory. Cache is a small amount of very fast memory located inside the CPU. It stores frequently used data and instructions for quick access. Why is this important? Well, accessing data from cache is much faster than RAM. Imagine cache as a student's desk. The most frequently used books or data are kept on the desk for quick access, while the rest are in the library or RAM. The closer the data is to the CPU, the faster it can be accessed. There are different levels of cache memory. Level 1 cache is extremely fast but small, usually between 2 and 256 kilobytes. Each core has its own level 1 cache. Level 2 cache is larger but slightly slower, typically between 256 kilobytes to 8 megabytes. Level 3 cache is the largest and slowest cache, usually 4 megabytes to 50 megabytes, and is shared between all cores. Think of level 1 cache as your pocket, but small, very quick to access. Level 2 cache is like your backpack. It's a bit larger, but takes a bit more time. And level 3 cache is like a locker, even larger, but slower to access. Having these 3 levels of cache helps the CPU work more efficiently. And here's a diagram of how the cache hierarchy actually works or looks in a CPU. Let's put this into practice. Which CPU do you think is faster? A dual-core 2.7 GHz processor with 4 MB of cache, or a quad-core 1.5 GHz processor with 8 MB of cache? To figure this out, think about clock speed, cache size, and the number of cores. A higher clock speed means faster processing. More cores means more tasks can be handled at once. And a larger cache means quicker access to frequently used data. So which one would you choose? Now let's move on to embedded systems. An embedded system is a small computer designed to perform specific tasks. It includes a CPU, RAM, and ROM, and is often used to control devices. For example, a microwave often has an embedded system that controls the timing, temperature, and power levels for cooking food. Without embedded systems, many of the devices we use every day wouldn't work. Let's look at some examples of embedded systems in cars. Modern cars are packed with them. For instance, cruise control maintains a set speed without driver input. Infotainment systems combine entertainment, navigation, and information. Rear cameras and remote parking assist with parking and reversing. These systems make driving faster and more convenient. For example, Automatic braking systems are embedded systems used to detect obstacles and apply the brakes if necessary. Here are some additional examples of embedded systems in cars. How are embedded systems different from general purpose computers? Well, embedded systems are designed for specific tasks, often with limited resources. In contrast, general purpose computers, like your laptop, can run a wide range of programs. For example, a dishwasher's embedded system only controls washing cycles, while a laptop can run games, browse the web, and more. Another example is a smart thermostat, which is an embedded system that controls heating and cooling, while a smartphone is a general purpose device that can run apps, take photos, and more. Here's a table highlighting embedded systems versus general purpose computers. Let's recap what we've learned. The three main factors affecting CPU performance are clock speed, cache size, and number of cores. An embedded system is a computer system used to control mechanical or electrical systems. Examples of embedded systems include sat-navs, microwaves, and dishwashers. Now it's time for some questions. Why is cache memory important for CPU performance? How does your quad-core processor improve performance compared to a single-core processor? Can you think of other devices that use embedded systems? Feel free to pause the video and think about these questions or discuss them with a friend. Let's look at some real-world applications of these concepts. Clock speed. So gaming PCs and servers often have high clock speeds to handle complex tasks quickly. Cache size. High performance laptops and desktops have larger cache to speed up data access. Embedded systems, smart home devices like thermostats, security cameras, and voice assistants rely on embedded systems. These technologies are everywhere, making our lives easier and more efficient. To wrap up, here are the key takeaways. CPU performance. So clock speed, cache size, and number of cores all play a role in how fast a CPU can process data. Embedded systems. These are specialized computers used in everyday devices to perform specific tasks. Real-world examples. From cars to microwaves, embedded systems are everywhere. Thanks for watching, and I hope you enjoyed learning about CPUs and embedded systems. Don't forget to like, subscribe, and leave a comment if you have any questions. See you next time.